Hi, I am Nikos Giavellis from Northeastern University, and this is our work on efficient computation of quantiles over joins. This is joint work with Nofar Karmeli, Wolfgang Atterbauer, Benny Kimmelfeld, and Mirek Riedewald. The recording that you are about to watch is from the PODS conference 2023.
Join queries. This means that we have a join over our database and the desired ordering of the output of the join. A quantile join query receives as an input also a relative position, and it returns the answer at that specified position on the array. Now, what is the challenge here? The output of the join can be very, very big, right? So if we have n tuples in our database, the size of the output of the join can be n to the power of d for some d that depends on the specific query that you have. The main question that we are asking in this work is, when can we find the quantile without actually computing the join? So as a more concrete example, think of a social network where we can have users making posts about events. So we can have a user attending an event, we can have a user sharing an event, or administrating an event. And if we're interested in this particular pattern, we may want to get statistics about it, right? So instead of computing all the possible patterns in our network, we may want to find the median occurrence of the pattern. For example, to know how many likes does the median occurrence of the pattern get. For that, we would write a join query where that would put the tables together, assuming we have our data in these tables, and then we would have to specify a ranking function. So here we have the number of likes both for the share relation and the attend relation, and we can choose to add them up for our ranking. We can take the maximum number of likes or something else. And the median query answer would then be just a specific combination of users, an event, and the likes. Right? What we saw in this work is that we can evaluate this query in time n polylog n, even though the size of the output of the join is n to the power of 3 in the worst case. So to put things together, we need two things to define our problem. We need a join query, and we need a ranking function. The ranking function can be a sum, a minimum, a maximum over weighted attributes, or it can be some lexicographic order. And the definition of our problem of a quantile join query is that we receive as an input a database and a relative position, and as an output we give the query answer at that position in the sorted array of query answers. Since we don't want to materialize the output of the join, we want the running time to be independent of this n to the power of d, and we set n polylog n as our target complexity. Alright, so let's look at some prior work and background, some very quick things that this audience is familiar with. A join query can be represented by a hypergraph, where the hyperedges are the atoms of the query. And a join query is acyclic if we can construct a join tree, where a join tree has the relations, the atoms of the query as the nodes, and the nodes that contain the same variable are connected. And we heard a lot about self-joins from Nofar. A query is self-join free if no relation appears twice in the query. Okay, so we have studied a variant of this problem in one of our previous works, and we gave dichotomy results for two specific ranking functions, sum and lexicographic orders, which is denoted by lex here. Some quick things about the lower bounds that I will keep assuming for the rest of the work is that they assume that we don't have self-joins, so it's only for self-join free queries. And also they rely on some hardness hypothesis in fine-grained complexity, which we can talk more about if you want. But I will keep assuming these two things. So what does the dichotomy say? If we have cyclic queries, then we can't support any order, neither sum nor lex, for example, for the triangle query here. For acyclic queries, we can do any lexicographic order, but we cannot do sum. And an example is the free path query that I have here. And if we want to be able to support sum, we have to restrict ourselves to queries with maximal hyperedges at most, which are at most 2. And maximal here means just that the hyperedge is not strictly contained in another one. Alright, so the question now is that the end of the story? Or is there more to do? There are a couple of things we are unhappy about. And the first one is that the tractable cases for sum are very, very limited here. It's essentially only binary joins. Another thing we're not happy about is that the algorithms that we use in this previous work are very specialized to these two ranking functions. And if we wanted to do another ranking function, then it's not really clear how we would do that. And in this work, we address these issues. So we'll move on to give a brief overview of the new results of this work. We develop a quite general framework that can support different ranking functions, and we use that framework to establish all the new results I will be talking about. The first one is about min and max as ranking functions. And we saw that for min and max, all acyclic queries are tractable. And so if we go back to the previous dichotomy, essentially we saw that min and max are at the same level of hardness as the lexicographic orders. And just as a quick note, our framework can also recover the old results we had about lexicographic orders and sum. So that's the first result. And then we started thinking about how can we do more things with sum, which seems to be the hard case. And one thing we did was to consider partial sums. So the previous dichotomy essentially assumes the worst case for every query, that all the variables participate in the sum. And a partial sum means that only some of the variables may participate in the ranking. So essentially we refine the previous dichotomy by taking this into account. And for the positive side of the dichotomy, we use our framework, and that's important because the previous algorithm was very specific to two relations, because it relied on an older result on matrices, which are two-dimensional. And for the negative side, we prove some conditional lower bounds. And we have a dichotomy for partial sums. And there are three conditions that the self-join free query has to satisfy. And to understand what they are, let's look at some examples. So if we have a query like this one here, the previous dichotomy would say, oh, I have three maximal hyperedges, I can't do that. That's not possible. But actually, if you have a sum that uses only A and C in the sum, then we now show that it is in fact tractable. Some negative cases now is that if it's cyclic, then we can't do it. In this query here with ranking A plus C plus E, these are three independent variables in the sense that they don't appear together in the same hyperedge, and this means that we can't do it. And finally, this one here with ranking A plus D has a chordless path of length 4, which is the third condition in the dichotomy. Chordless means that only consecutive variables in the path appear together in the hyperedge. So that's our second result, the partial sums. But it's still not entirely satisfying because still the class of queries where we can do this efficiently is rather small. So we started thinking about approximation. The previous dichotomy was only about exact results, but now we introduce approximation to overcome the hardness of sum. So we modify now the definition a little bit and we say, okay, I also receive as an input an epsilon, and this epsilon allows me to return any answer that is in the range of plus minus epsilon from the desired answer phi here. So, for example, if epsilon is 1%, and I'm asking for the median, I can return any answer from the 49% to 51% range. And we saw that with this definition, we can actually handle efficiently all acyclic queries. So that's our third result with approximation. Alright, so Now, I want to say a few things about this framework that I've been talking about. What is it and how do we use it? So if we go back almost, actually exactly 50 years ago, there is a fundamental algorithm which is called linear time selection. And selection there means essentially the same thing, that we want to retrieve the kth answer in an array. So here we don't have a query and a join, we just have a simple array and we want to find the kth answer. And the algorithm works very roughly in the following way. Let's say we want this index k. The algorithm is going to choose a pivot element, and there is a way to choose the pivot, but let's ignore that for now. We choose pivot, and we use the pivot to partition the array into two splits. One that is less than our pivot, and one that is greater than our pivot. And now if we count how many elements is in each partition, we can find where our desired index falls into, which is the left partition here. So we only keep that part of the array, and we keep doing the same thing until we have few elements left. That's basically the algorithm. And we want to apply the same high-level idea now to our join queries. But there are a couple of key differences. The most important one is that we don't actually have the array. We don't want to materialize the array of query answers, and that makes things difficult. The second difference is the complexity target. So we don't want to just remove a log factor from sorting, but go from polynomial complexity to quasilinear. And also we can use this algorithm, because this algorithm exists, of course we can use it as a subroutine. Okay, so let's think about how can we apply this idea now to join queries. And let's look at the steps of the algorithm that we just saw. First of all, we need to be able to select a pivot. A pivot for us is going to be just a query answer, but it needs in some way to be a good pivot. Essentially, a good pivot is one that eliminates a constant fraction of the remaining answers at every step. Also, if you remember, there was a partitioning step where we split the array into two pieces, and we need to be able to do that also. But that's difficult now because we don't have the array. And to solve that, we introduced this idea of trimming for the partitioning. You can think of the partitioning as introducing an inequality to the query. So if our ranking function is a plus b, the inequality is going to look like this: a plus b less than the value of the pivot for the ranking function. And we want to handle that inequality essentially by removing it from the query. So we start with our original database and our query, and we want to construct a new database and a new query that satisfies the inequality. That's trimming. And the third step, which is kind of trivial, is that we also need to be able to count the answers in every split. But for acyclic queries, it's well known that this can be done in linear time, so we are okay with that. So essentially, to summarize, our framework for every ranking function needs to have these two sub-procedures: pivot and trim. And for pivot, we have a quite general solution. So we give a linear time algorithm that selects a good pivot for all ranking functions that we call subset monotone. And these include all the ranking functions that we saw: sum, min, max, lexicographic orders. But the trimming is actually the difficult part. And for this one, we don't have a general solution. We have a customized construction for every ranking function. And this is actually where the approximation comes in, right? So for sum, for the sum ranking function, we can't have a trimming procedure in general, but we saw that if we have an approximate solution for trimming, this leads to approximate quantiles. And a lossy trimming is one essentially where that eliminates more answers than it should. So we lose some extra query answers that satisfy the inequality, but our trimming removes them. But we saw that if their number is bounded, then also the approximation of the quantile will be bounded. And just to give you a flavor of how the algorithms look like, I will talk a little bit about the pivot selection algorithm, just the high-level idea. So this is a message passing algorithm that operates bottom-up in the join tree. Very roughly, we materialize a relation for every node of the join tree, and we compute a pivot for every tuple in these relations. That is a pivot for the subtree. Right? So every tuple computes a pivot for its subtree, and we send those pivots up the tree and we combine them. Right? So if we look at this leaf here, we are grouping by the joining attributes, which is C for this leaf, and we are taking the median for every group. And we do the same for the other leaf, and when they reach the parent, we combine them and take the median again. So essentially at every step, at every level of the join tree, we keep taking the median of the median of the median until the root computes, until the root sends a single value, which is going to be our pivot. That's just a high-level idea of the algorithm. You can come to the poster if you want to learn more about it. Okay, so that's our work. To conclude, we give this general framework that essentially, if the ranking function that we consider is appropriately monotone, it reduces the problem of quantiles to the much simpler problem of trimming an inequality. And we use it to establish these three results that you can see on the right side. So we saw that min and max work for all acyclic queries. We have an approximate solution for sum for all acyclic queries, and we also expand the tractable cases for the exact sum by considering partial sums. In all of these cases, we can find the quantile without computing the output of the join. And the next step will be to actually implement this and see how it compares against database systems that are going to actually materialize the output of the join, and we can expect them to be very slow. And finally, I would like to mention that in this work we didn't consider projections. But if we have conjunctive queries instead of join queries that have projections, then we can handle them as long as they belong to the free connex class. But certain lower bounds for non-free connex queries in particular are still not 100% clear. That's the end of the talk. Thank you for listening.